Hi, good morning, everybody. Welcome to the track HPC session 1. It's a pleasure for me to start this session with the presentation of Rafael Mayo-Garcia from the Technology Department, CIEMAT, Madrid, Spain. So the title of his talk will be Energy Consumption Studies of the Weather Research and Forecasting Executions with the Limitless Monitor. I think this is a very interesting talk, especially because of the recent Nobel Prize announcement related with the, in physics, related with the modeling of air climate, quantifying variability and reliability, predicting global warming. So it will be a real pleasure to hear Rafael Mayo about this topic. So welcome, Rafael.
Thank you, Luis. I'm going just please let me share my screen. Okay, so let's move on. As you have mentioned, Luis, I am going to present on behalf of the authors just this work regarding the energy consumption studies of the well-known WRF code with the limitless monitor that has been developed by the team. This is a joint work already developed by the Arcos group at the Universidad Carlos III de Madrid and CIEMAT. So, which has been the motivation for this work? We were surprised that there is a lack of understanding of the power consumption characteristic of high-performance computing jobs which run on production high-performance computing systems. We are much aware of a lot of benchmarks and tests and this kind of stuff that are usually presented when a new supercomputer or a new code is released, but not so much on real production high-performance computing systems when the load must be shared among several users. In this case, we just selected WRF, which is a widely used code for weather forecasting and climate research as case study, and you know that it is based on MPI communication scheme. For making the measurements of temperature and energy, we use the limitless monitor. I will briefly talk about it later on. And the tests were executed on a partition of our cluster at CIEMAT called Shula. You can see there the characteristic of which. And it is important to mention that in this Shula supercomputer at CIEMAT premises, there are a huge number of work executions by several groups. So it is of much importance for us to profile the real execution environment of this code on our cluster. A brief introduction about WRF, which stands for Weather Research and Forecasting. It's a production code for weather and climate research, which is used widely in both research and development centers and in industry. It is physically complete. It can solve a lot of characteristics, and it is on a modular basis in which the code has been implemented, so new physics can be easily adapted and included, and this is massive parallel. In this case, we have selected two modules, two cases which are related to the planet boundary layer. You can see there their names, YSU and MIN. These specific modules have been implemented by CIEMAT researchers working on wind energy. The monitor that we have used is limitless. I have mentioned it before. It's an HPC monitor in production status developed by Universidad Carlos III de Madrid. And we just configure it to measure energy every 5 seconds. I guess I can tell you that it is a very lightweight monitor with outstanding results. It is able to perform measurements in a very short time, so an outstanding high frequency, just below 1 second if needed. But for the energy purposes of this work, we just monitor the results every 5 seconds. You can see there the different structures of the monitor and how they have been integrated in the Shula nodes. There is a diamond monitor for just getting the different parameters and measure it. An aggregator for just compiling all of them, and a server which hosts the different information previously to the database log. The modules that I have told you before, we have measured firstly a strong scaling study in order to know in which environment and in which performance we are moving. So in this sense, we varied just the number of nodes and the number of processes per node. So let's say the number of MPIs per nodes. We just move up to 8 reserve nodes, which are by processors, all of them, and we just repeated every test 3 times. We did not move forward because we just found an error rate much low. You can see there, just around 1%. So we decided not to consume more resources of the Shula supercomputers, as we get a very good statistics. So we just got 166 runs in total. This is the results for the execution times of the 2 modules, just executing 2 processors per node. So we just, the number of MPI processes run up to 16, 8 by 2. And you can see there how the time is being reduced. We just repeated the strong scaling scheme that I have showed you before in this previous slide. You can see that somehow it's a typical scaling of certain MPI applications in which there is a reduction in the execution time as the number of nodes increases, but at the end there is a time in which there is a saturation and the results just get worse. So a similar result as this one for 2 MPI processes per node, we just also made it for up to 20 processes per node, and you can see also the execution and the result that we have found there. And from this point on, we just moved to the energy in order to know how to characterize the energy consumption in the clusters. This is again the same result for 2 MPI processes per node, and you can see there that more or less it follows a linear behavior in which the energy is increasing as the number of MPI processes grow. Same results can be also applied to the case in which 20 processes per node were executed. So at the end, we just were able to plot this scatter figure that you can see there for the 166 experiments. And you can see there how the different executions behave in terms of the energy consumption and the time. You can see there a table which the optimum results for the different tests and the different 2 modules of work for 1 and 8 node and the different number of processors, and you can see there the execution time and the energy. From that point on, we were able to move to some outcomes that have been just really surprising, at least for me. You can see there that just in conclusion, small increments in the computation times could lead to the energy savings. And for example, for the mean mode, just an execution of 6% in the time can produce an energy savings of 9 times. And for the YSU module, the execution time increasing of 20% could lead to an energy savings of 7 times the previous one. So they are very surprising results, at least for me, and can drive us to some final conclusions that are just depicted in this slide. As I have mentioned and I have explained, we have made a study of the energy consumption of work runs with limitless 2 input cases just on strong scaling, which is not so good in principle. And we have just run the experiments under a parameter sweep paradigm. We have found out that there are important energy savings slightly increasing the execution time, which is very, very useful for a supercomputing as the one that we are hosting, because we must share our resources between different users in a way in which just the filling rate of the supercomputer, let's say the usage, is almost close to 100%. So just slightly increasing this performance in time consumed could lead to this energy savings. So at the end, it is very, very good for a supercomputer, just widely used and exploited by different users. In this sense, we think that this work paves the way for a useful study for production codes in the long term. I mean, we have made it for work, but we will do it in the coming future for other codes of interest to Tiamat, just highly exploited by our colleagues. And we can think that we can also profit from an dynamic allocation of tasks based on characterized uses and artificial intelligence methodologies. So in this sense, whenever we count on several codes already profiled in terms of a trade-off between energy consumption and time performance, it is possible to make studies on dynamic scheduling of tasks in order to achieve a better usage and a better energy performance in terms of the energy and the performance computation that we will need. So there is an open door and a future work to be carried out from the outcomes of this work. And with that, I just come to my end, and thank you so much, all of you, for your attention.
Thank you very much. Really interesting. And now we are open for questions. We have more than enough time. So if you have any questions, you can raise your hand, digitally, and you will be able to open or you will allow to open your microphone and to ask questions directly to Rafael Mayo. So if you have any questions, you can also write the questions in the chat. So this is another way to ask something. So any questions? No, it was so clear as usual from Rafael. No, any screen? No. No, I think there is no questions here. No, there is no questions. But Rafael, yes, finally, Carlos, I think no, there was someone raising. No, Miguel Tiempos. Yes, thank you very much, Miguel.
Hi, I'm sorry, I joined in just a little late from the previous call. Was this just on CUDA, or did we begin on WRF simulations yet?
No, it is on a pure-based GPU execution, not GPU one.
Oh, okay. Yeah, I'll wait a little later for WRF simulation topic. I got a couple of questions there.
Okay. Any other question? No? Okay. I think we already have the 15 minutes. So it was the perfect time for your presentation, Rafael. So I have to thank you. Thank you very much for this interesting topic, especially everything related with the weather research and forecasting. So it's interesting. So we will just move on to the next presentation, and this I will switch to Spanish just for the next presentation. So la siguiente presentación corre a cargo de Pablo Rojas. Pablo Rojas forma parte de la Universidad Industrial de Santander en Bucaramanga, Colombia. Y el título de su plática es A Methodology for Evaluating the Energy Efficiency of Post-More Architecture. Pablo, tienes los 15 minutos y al final una serie de preguntas. Adelante.
Ok.
Pablo. Gracias.
Ok, muy buenos días. ¿Pueden ver la presentación?
Sí.
Listo. Mi nombre es Pablo José Rojas Yepes y pues, se va a presentar el tema a presentarse pues, es una metodología para la evaluación de la eficiencia energética de arquitecturas post-Moore. En este trabajo pues, trabajamos en conjunto con el profesor Carlos Jaime Barrios y Luiz Angelo Steffenel. Bueno, como agenda, pues tenemos una pequeña introducción a la metodología, parte del estado del arte investigado, ya pues una descripción de lo que es la metodología y por último tenemos resultados de un caso de estudio y conclusiones. Entonces, pues ya desde hace un tiempo y de aquí a futuro en adelante, las aplicaciones van a ser las que determinen el hardware que que vamos a implementar pues, para desplegar dichas aplicaciones. Por esto, pues, es necesario una metodología en la cual la aplicación elija o seleccione los dispositivos con cuidado. Por esta razón, pues, se presenta la metodología ACS, considerando tanto las características y necesidades que tienen las aplicaciones, como la composición o el hardware que tenemos disponible para desplegar dichas aplicaciones. En el estado del arte que encontramos, pues hay bastantes implementaciones y evaluaciones de dispositivos post-MURT, pero en la mayoría, igual que por ejemplo en el primer documento, se presenta de forma implícita la metodología que utilizaron pues, para desarrollar estas evaluaciones y estas implementaciones. En el segundo caso, pues tenemos a Paradise, que sí es una metodología utilizada para evaluar estas tecnologías emergentes. Y en el documento presentado, pues ellos exponen cada una de las fases y de los pasos, pero lo hacen de una manera somera o superficial. Entonces hay que contactarse con ellos pues, para pedir una profundización o que ellos le den a uno una profundización en esta metodología, en el uso de la metodología. Y en el tercer caso, pues encontramos al Row Gallery, que es más que una metodología, es un banco en el que encontramos y en el que tenemos acceso a dispositivos y a evaluaciones o a herramientas para evaluar estos dispositivos. Y no, pues no se utiliza una metodología general, sino lo que se genera pues es una evaluaciones de metodologías de evaluación particulares para cada uno de los dispositivos presentes en el banco de pruebas. Por ello, pues entonces se plantea esta metodología ACS. Esta metodología pues consta de 9 pasos. Lo que es el primer y el segundo paso, podemos intercalarlos, depende de la situación en la que nosotros nos encontremos, podemos cambiarlos. Entonces, si contamos con una aplicación y queremos saber sobre qué hardware lo podemos desplegar, pues realizamos la selección de la aplicación y realizamos una caracterización de la misma aplicación, de las necesidades que tiene tanto de hardware, librerías, tipo de datos que maneja, y sobre eso pues se genera una documentación. Si fuera el segundo caso, que es que tenemos pues dispositivos disponibles y queremos ver qué aplicaciones podemos correr sobre ellos, pues también realizamos una caracterización, conocemos el dispositivo a fondo y podemos empezar a tener una idea de qué tipo de aplicaciones podemos desplegar sobre él. Una vez que ya tenemos esta documentación y estas características definidas, pasamos al tercer paso, que es pues una optimización de las configuraciones que le vamos a dar a la prueba. Y aquí pues si por ejemplo, si en la documentación o en la caracterización la aplicación se puede desplegar sobre los diferentes dispositivos seleccionados, pues podemos ejecutar la aplicación, o en esa caracterización pues van a salir los puntos críticos o los cuellos de botella de la aplicación y podemos utilizar pruebas sintéticas que generen pues esa misma carga de trabajo de esos puntos críticos para realizar pruebas sobre el dispositivo y ver si la aplicación no está o no se ha migrado a ese dispositivo, si es una buena opción migrarla. Entonces, una vez que ya tenemos el tercer paso listo, decidimos si la vamos a ejecutar o las pruebas sintéticas, definimos las métricas que vamos a utilizar y las banderas de configuración, sea para las pruebas sintéticas o para la ejecución de la prueba, y empezamos pues ya también a planear el flujo de trabajo que vamos a tener con cada una de las pruebas. Una vez que tenemos esto, ya pasamos al quinto paso, que sería lo que es la configuración o la puesta a punto de los monitores, sea monitores de consumo, monitores de recursos y cómo vamos a capturar los datos. Eso es más o menos lo que hacemos aquí. Una vez tenemos ya todo listo, podemos pasar al sexto paso, que es justamente la implementación del flujo de trabajo que nosotros hemos diseñado para las pruebas que vayamos a realizar. Una vez pues termina la prueba, viene el séptimo paso, que es pues, el etiquetado y almacenamiento de datos. Nosotros decidimos cómo etiquetar los datos para que se nos facilite el análisis, y también decidimos dónde almacenarlos de manera tal pues que nosotros mismos tengamos una seguridad de que esos datos no se nos van a perder, ni tampoco que se nos van a confundir con las etiquetas que le demos. Una vez terminamos la prueba, pues pasamos al octavo paso, que es repetir la prueba la cantidad de veces que nosotros la consideremos necesaria para pues tener una buena base y entender el comportamiento que tiene el dispositivo y la aplicación. Una vez que terminamos pues las repeticiones, podemos pasar a seleccionar nuevas pruebas en el caso de que tengamos varias pruebas para el dispositivo, o cambiar la configuración de la ejecución de la aplicación y ver pues cómo se comporta bajo esas nuevas configuraciones el dispositivo. Una vez que ya terminamos todas las pruebas que hayamos planeado, pues finalizamos el octavo paso y pasamos a lo que es el análisis de resultados. Como caso de uso, se selecciona una aplicación que tiene 3 cuellos de botella o 3 puntos críticos, que son generar múltiples hilos cuando se ejecuta, la asignación y reasignación de espacios de memoria cuando se ejecuta, y un fuerte componente de computación de trabajo con números de punto flotante o números flotantes. Y esta aplicación, pues, por ahora solamente trabaja sobre CPU. Para el caso, pues teníamos 2 dispositivos a la mano, que era un dispositivo embebido y un dispositivo de escritorio. El dispositivo embebido, pues, es una Jetson Nano, y el dispositivo de escritorio, pues, es una PC. Ambos dispositivos cuentan con CPU, GPU y RAM, así que podemos desempeñar otras pruebas para otras aplicaciones sobre estos dispositivos. En el caso pues, de la Nano tenemos un procesador ARM de 4 núcleos. En el caso de la PC tenemos un procesador de x86 de 6 núcleos. Y contamos en la Nano con 4 GB de RAM y en el caso de la PC con 16 GB de RAM. Una vez que ya tenemos definidos los dispositivos, pues pasamos a seleccionar 3 pruebas para justamente ejercer esta carga de trabajo que es crítica en la aplicación. Entonces seleccionamos 3 pruebas que son Pthread, Cfloat y malloc. En el caso de Pthread, pues se generan n trabajos de manera iterativa en la cual se crean y se terminan múltiples hilos. En el caso de Cfloat, lo que hace la prueba es una mezcla de operaciones complejas de punto flotante, y en el caso de malloc, pues se generan n trabajos en los cuales se asigna y se reasigna y se libera memoria. En cuanto a las métricas de evaluación, tenemos 2 métricas que son rendimiento y justamente pues eficiencia energética, que vendrían siendo las operaciones por segundo y las operaciones por vatio para el caso de la eficiencia. La configuración de las pruebas para Pthread se ejecuta con 4 hilos, con 4 trabajos y 1024 hilos. En el caso de malloc, pues se ejecuta con 4 trabajos, y en el caso de Cfloat se ejecuta ejerciendo la carga sobre 1, 2, 3 y 4 cores. Como resultado pues, de esta configuración y de estas pruebas, Pthread y malloc para la PC pues, tienen un muy buen rendimiento, y esto se debe a que cuando se ejecutaron las pruebas se evidenció que estas pruebas utilizaban todos los recursos disponibles que tenía el dispositivo. Entonces, en este caso, pues teníamos más cores y más hilos y teníamos muchísimo más RAM. Por eso tenemos esa ganancia en rendimiento. Pero ya en el caso de la prueba de Cfloat, tenemos un comportamiento muy similar entre las dos CPUs. Solo se ve pues una pérdida de rendimiento cuando se utilizan los 4 cores en el caso de la Jetson Nano, pero esto se debe a que empieza una competencia por recursos entre el sistema operativo y la aplicación o la prueba que estamos realizando en ese momento. En cuanto a la eficiencia energética, las pruebas pues muestran que la Jetson Nano, a pesar de que no tiene el rendimiento de la PC, pues sí tiene una mayor eficiencia en realizar cada una de las pruebas. Para el caso de Pthread y malloc, tiene una eficiencia de más o menos el doble de la eficiencia presentada por la PC, y en el caso pues, de las pruebas de cómputo de flotantes, tiene una eficiencia de 6-7 veces el cómputo de la PC. Como conclusiones, pues podemos decir que la metodología ACDC pues, simplifica la documentación de evaluaciones de arquitectura post-MURT, ya que pues, a medida que vamos desarrollando cada uno de los pasos, vamos generando un documento y vamos generando listas que nos facilita pues, la construcción final de algún documento que nosotros queramos presentar, o libro que queramos mostrar sobre la evaluación o el proyecto de investigación que nosotros estemos realizando. También, pues a medida que se realizan el paso a paso de la metodología, se van generando avances a medida que se realizan las iteraciones de las pruebas, se van generando avances y esto pues contribuye a ir mejorando o a ir afinando la configuración de las pruebas para ir mejorando los resultados que esperamos pues de la evaluación que estemos realizando. Y por último, pues la metodología ACC se puede adaptar para satisfacer cualquier métrica que nosotros deseemos evaluar y cubrir las necesidades de cualquier aplicación que nosotros seleccionemos o cualquier hardware, o hardware o dispositivo que tengamos a la mano y queramos evaluar. Muchísimas gracias.
Muchísimas gracias, Pablo.
¿Preguntas?
¿Alguna duda? ¿Preguntas? Haríamos lo mismo que en la plática anterior. Si tienen alguna pregunta, podrían levantar la mano de forma digital o podrían escribirla. Esteban, tenemos una pregunta de Esteban.
Hola, muchas gracias por la presentación, Pablo, estuvo interesante. Hay algo que no termino de entender, es un problema, solamente problema mío de captación de las ideas, ¿no? Pero yo me imagino haciendo las pruebas que hago normalmente cuando tengo que ver una aplicación si funciona en cierto equipo, no se diferencia mucho de lo que vos contaste. Entonces, me gustaría si me podés dar un ejemplo o estresar cuál es la parte diferente de contar, digamos, de esta metodología respecto a lo que, no sé, yo suelo hacer habitualmente cuando desarrollo una aplicación o pruebo una aplicación en una máquina por primera vez o ya, o los distintos casos para ver qué es lo que no hago, qué es lo que no hacía antes que me estás proponiendo hacer ahora con esta metodología.
Bueno,
Gracias.
esto va mucho también en cómo se documente la persona. Hay muchas personas, o bueno, nos pasa con los estudiantes de pregrado, que ellos quieren hacer pues su proyecto y quieren ejecutar una aplicación y ellos entran a intentar instalar la aplicación con todas las paqueterías, con todo, y entran a intentarla instalar sobre la máquina. Pero es muy probable que, por ejemplo, ellos quieran probar dispositivos de hardware abierto o sobre lo que quieren desplegar, y si no conocen, pues cómo funciona. Muchas veces sucede, y a mí me ha pasado, que cuando yo intento desplegar ciertas pruebas, no se pueden realizar sobre ese hardware. Por ejemplo, me pasó que estaba haciendo pruebas con contenedores sobre dispositivos embebidos y las pruebas que yo iba a hacer eran sobre GPU. El problema es que tanto Docker y Singularity tienen ciertas fallas con la ejecución de esas GPUs y si yo me hubiera documentado bien, no hubiera llegado pues a proponer esas pruebas, sino pues yo ya hubiera sabido que no las iba a poder realizar o que si las iba a realizar pues iba a tener que solucionar ciertos problemas antes de poderlas ejecutar. Y así pues ha pasado con otro. Entonces primero o sea, lo primero que se busca es que la persona entienda con qué va a trabajar, qué aplicación es la que va a desplegar, qué tipo de datos maneja, si está compilada para las diferentes arquitecturas, porque puede pasar de que está solamente para x86 y se quiere, por ejemplo, se quiere hacer la implementación, por ejemplo, para ARM o ARM64, entonces entran pues a intentar compilarla y se ve pues digamos un impacto negativo, o sea, una reducción en el rendimiento, pero si ya se ha hecho pues una caracterización de la aplicación, se sabe cuáles son los puntos álgidos o los puntos críticos, entonces lo que se puede buscar es buscar cargas de trabajo con pruebas sintéticas, en vez de hacer todo el proceso y todo el trabajo de intentar pasar la aplicación, primero probar cómo va a ser el impacto sobre esas cargas, sobre esos dispositivos, y luego entonces de ver los resultados, sí es opcional, o sea, sí vale la pena hacer esto porque tenemos pues una ganancia o tenemos un rendimiento parecido con un equipo, por ejemplo, de escritorio o un equipo de propósito general, pues se podría ya empezar a hacer la migración, pero no se entraría sin conocer el terreno. Esa es la propuesta de la metodología. Antes de entrar a trabajar, primero pues investigue bien el terreno a ver si vale la pena o no invertir el tiempo en esa migración o en ese desarrollo. Creo que Esteban está
Sí,
muteado.
sí era. No sé si se bloqueó el micrófono.
Sí, está alzando la mano, pero... Ah,
Ahí
listo, ya.
está, sí, no me permitía desmutearme para continuar, gracias.
Ok.
Entonces, ahora, el foco está puesto en el título, en lo que están contando, en esto de las nuevas arquitecturas, post-more arquitecturas, nos gusta poner esos nombres divertidos a las cosas. En este sentido, digamos, el énfasis estaría entonces en... Yo para ver si entendí bien, ¿no? Entonces, en documentar, en tener documentación generada para compartir con la comunidad, para uno mismo, o sea, uno documenta los test, los resultados, y la idea que esta metodología lo que propone es una forma mecánica de hacer eso como para que quede esta información disponible. ¿Sería por ese lado digamos, el novelty de lo que están proponiendo?
Sí, y lo otro es, o sea, no solamente es para evaluar eficiencia energética, también se pueden colocar las diferentes métricas que se quieran medir. Entonces, no solamente se enfoca, por ejemplo, si la aplicación no tiene un componente, por ejemplo, de CPU, sino tiene un componente de GPU, entonces la métrica se enfocaría al componente que vayamos a hablar de la GPU, por ejemplo, flops por segundo o cantidad ¿cómo es? El trabajo de las neuronas, el tiempo, pues, por ejemplo, del entrenamiento,
Ujú.
esas serían las métricas. Entonces, no se casa con una sola métrica, sino pues le da la libertad al investigador que pues siguiendo esta secuenciación vaya él documentando y lo adapte a lo que está construyendo para que sea muchísimo más fácil después sacar un paper o sacar un libro de la investigación.
Ok, muchas gracias, Pablo.
¿Vale?
No quiero robarte más tiempo porque si no soy yo solo.
Gracias, Esteban. Tenemos otra pregunta en el chat, que es, ¿qué herramientas usaron para obtener la métrica de la energía?
En este caso, en esos momentos, pues no se había pulido tanto el JTOP, que por ejemplo es una forma de uno poder sacar las medidas en la Jetson Nano, y pues tampoco tenía yo una forma de medir internamente el consumo del dispositivo del PC. Entonces lo que utilicé fue un tomacorriente inteligente. Él va haciendo un historial, y lleva un historial del consumo del dispositivo que esté conectado. Entonces yo lo que hacía era, pues ponía yo a punto los monitores, ponía yo a punto el medidor de consumo, y hacía pues una captura de esos datos, tanto de consumo como de la ejecución de la prueba. Y así pues era como yo obtenía los datos.
Perfecto. Espero, Luciano, que haya sido respondido la duda que tenías. Pues creo que por el tiempo te agradecemos mucho esta plática, esta interesante plática, Pablo. Y bueno, pasamos a nuestra tercera plática del día de hoy. So, next talk is from Alexandre Sena. Alexandre Sena from the University of the State of Rio de Janeiro, Brazil. And the title of this talk is An Efficient Vectorized Auction Algorithm for Many-core and Multicore Architecture. So, Alexandre, you have 15 minutes. And at the end, a couple of questions.
Okay, thank you, Luiz. Are you hear me?
Yes,
Can you hear?
I can hear you and I can see your presentation.
All right, good afternoon, everybody. My name is Alexandre Sena, and I'm an associate professor at Universidade do Estado do Rio de Janeiro, and the other co-authors are Professor Aline Nascimento from Universidade Federal Fluminense, and my PhD student, Márcio Silva. So that's the talk outline that I'll present. The auction algorithm is widely used to solve bipartite graph matching problems. And the main reason that it's used is that because it produces the optimal solution, and its distributive nature of the algorithm allows many parallel implementations. And this algorithm quite used in bioinformatics and computer vision. On the other hand, multi-core and many-core are highly available platforms that you can find in many laboratories and computing centers. But to use these platforms efficiently, we need to use the single structures available and also the multiple cores. In this context, this work, the objective of this work is to propose an efficient, scalable vectorization of the auction algorithm for these architectures. So we implemented a completely vectorized version for 512 bits Singh registers. And we also detailedly evaluated the implementation. It is a scalable implementation and can be easily adapted to new architectures with larger instructions. We also evaluated a parallel implementation in conjunction with the Singh instructions, and we saw that we exploit the full potential of these architectures for the auction algorithm. So now we talk about the auction algorithm problem. At first, it was designed to assign n persons to n objects and maximizing affinity, maximizing cost. So basically, it's a loop, and at each iteration of the loop, it tries to assign person to objects. While it did not assign every person to an object, it will stay in the loop. And at each iteration of the loop, we have a bid phase and an assignment phase. In the bid phase, the person gives a price to the object, gives a bid to the object. And in the assignment phase, the person who gives the highest value is assigned to this object. Now I talk about the vectorization that we did. But first, why do we need vectorization? Because these multi-core and many-core machines have these specialized Singh instructions that can increase the application performance only if you have a good vectorization of the application. What's a vectorization? It's basically converts a scalar implementation into a vector process. So instead of executing instruction with one position of our array, we executed for 8 or 16 positions of an array at the same time. But the compiler sometimes is able to vectorize the code, but only if you have a simple optimized code. And there is no guarantee that the auto compilation, the auto vectorization of the compiler will be the best option. So when the compiler fails to vectorize a code, or the user wants a better vectorization, you have two options: explicit vectorization or Singh instruction programming. In the explicit vectorization, it's basically using pragmas in OpenMP programming model. And the Singh instructional program, it's a low-level program called intrinsic program. In this work, we used Singh instruction program to achieve a complete vectorization, a complete efficient vectorization of the auction algorithm. So now I show a small part of the vectorization of the code, because in the paper we have the complete vectorization, but here you do not have the time to explain everything. So I show the idea. Here on the left side, we have the code, a simple code for find the highest value in our array and its index. So it's a simple C code, everybody knows. On the right side, we have the vectorization of this code. Basically, what we try here is to avoid a conditional statement. And instead of iterating one by one in the array, we try to execute many instructions at the same time. For instance, in this sample, we are executing 4 instructions at the same time using the vectorization of variables. In the 512-bit Singh instruction that we implemented, instead of 4, we executed 16 operations at the same time. So basically, we change conditional if condition to some logical operations that do the same thing. Find the highest value of array and its index. And another interesting aspect of the vectorization is this if count here. This if, instead of applying only one position of the vectorized instruction, we are applying in the whole instruction. So if we do not execute the instructions in this if conditional, we are avoiding 4 instructions at the same time for each one of these instructions. In the end of the vectorization, we have a vectorized variable in this sample with 4 positions. So we have to do a reduction to achieve only the highest value. Instead of 4, we will reach only the highest value. It's a normal procedure. And to take advantage of the full potential of the multi-core and many-core architectures, we have to not only use the Singh registers, but also the multiple cores available. And in this work, we implemented the OpenMP code. It's basically using two parallel fors, one for the bid phase, another one for the assignment phase. The bid phase and the assignment phase are very, very parallelizable. So it is very simple to do that. Now I will show part of the experimental analysis that we presented in the paper. We use two machines, one many-core machine and another one a multi-core machine. And an important aspect of the analysis is that the same vectorized code and parallel code were executed in both machines. I only had to compile for each one of these machines. So first, I will show you some results of the vectorization. So it's the vectorization only. So in this execution, I used only one core of the many-core machine and only one core of the multi-core machine. And you can see here the original execution time, and the vectorized execution time. And you can see that the speed up was very good. We achieved a very good speed up. On average, for the many-core machine, we had more than 20 average speed up. And for the multi-core machine, we had more than 14 of speed up. You can see that for AFL instance, we have a very low speed up. The reason is because if you see the number of lines and columns and the number of iterations, it's a very small problem, a very small matrix. So that's the reason for that slow, that very bad speed up. Now I talk about the full result. I mean, the parallelization in conjunction with the vectorization. And if it's scalable, so we increase the size of the problem. You can see, have 2K, 4K, 8K, 16K. And we show the original time, the vectorization time, and vectorization plus parallelization time. If you see that in green, the execution time for the vectorization plus parallelization, it's a very good time. So the speed up was 138. And for the larger matrix, for the many-core architecture, was 751 speed up. That's very good results. On the other hand, for the multi-core, the results were not so good. We achieved 16 for the smaller matrix and 82 for the larger matrix. The reason for that results is that we have more work to do in the many-core machine than in the multi-core machine regarding the time that the frequency of the two architectures. In the many-core, we have a low frequency, and so we have more work to do. But if you can see the time to execute, the 20 seconds, 20.99 seconds for the larger matrix in the many-core, and 36 seconds for the multi-core. So the execution time was not so distant. It was a little worse in the multi-core but not so distant. And another reason for the bad behavior of the multi-core machine, I'll show you now in this experiment. The frequency of the architecture varies according to the increase in the number of cores used. For instance, when we use only one core, we achieve 3.5 gigahertz. And with 32 cores, we achieve only 2.7 gigahertz for the AVX2 Singh instruction. And when we see the same experiment for the AVX 512, with 32 cores, we achieve only 2.5 gigahertz. So we can see here that the architecture has to clock down its frequency when it has risk of overheating the architecture. So it's not so scalable as the many-core architecture. The multi-core architecture is not so scalable. Finally, on conclusions, to take advantage of the full potential of many-core and multi-core architectures, we have to exploit the Singh registers and the multiple cores available efficiently. So in this work, we implemented and evaluated a parallel vectorized auction algorithm, and results show an excellent performance of the vectorization, achieving very good speedups, both for multi-core and many-core machine, showing that it's capable of exploit the full potential of these architectures. Thank you.
Thank you very much, Alexandre. It was not only the results were very good, but also very educative, your presentation, because of the examples you presented. So thank you. And now we have time for a couple of questions. As before, if you raise your hand or if you write your question, it will be okay. We have a questions here in the chat. Where can we find the paper? That means they are asking for the paper.
Yeah, I think the paper will be available after only after the conference. But I have another papers of this work, and if you look in the internet, my name is Alexandre Sena, and vectorization auction algorithm. And if you want to send me an email, I will put in the chat my email.
Yeah, it's interesting because you have another couple of examples about how you vectorize it. So, yep, will be great to have your paper. We have another question, is what is the main focus of your research that you can optimize the vectorization techniques? From Miguel Tiempos. And also,
in this paper, the main focus was to present a full vectorization of the auction algorithm for both multi-core and many-core architectures, and taking the full advantage of the 512 bits Singh registers. But the vectorization is scalable, so if we have 1024 Singh registers next month, it's very easy to adapt using the programming because the instructions are very similar from one architecture to another, from AVX2 to AVX 512, and so on. I don't know if that's the question.
Well, yes, remember that you can also raise your hand, I think, but we have another question from Fernando Fursato. It's about the throttling. Do you think another clock, better cooling will fix that?
Yeah, I don't know. It was something that new for me when I was analyzing the performance of the application, and I realized that the clock down of the architecture, that's an Intel problem. I don't know. I'm curious because I saw the professor from Japan talking about the supercomputing. I think the AMD chip may be much better than the Intel chip too, and it has 512 bits. Singh registers also.
Okay, perfect. Thanks for the answer. Alexandre already write his email, so you can write him or ask him for the paper. So thank you very much again, Alexandre. We will move on to the next talk. But thanks again. So the next talk is in charge of Jorge Lozoya. He is from the School of Engineering and Technological Innovation from the University of Guadalajara, Campus Tonalá, Jalisco, here in Mexico. And the title of his work is Green Energy HPC Data Centers to Improve Processing Cost Efficiency. So Jorge Lozoya, thank you very much for your presentation. And you, as before, you will have 15 minutes. And at the end, you will have time for a couple of questions. So thanks in advance, Jorge.
Thank you very much, Luis, and for all the people. Well, let me share my screen. Can you see my presentation?
Yes. Perfect.
Okay. Well, thank you. This research is made by me and Carlos Gesal Vega Gomez, Alberto Coronado from the Centro Universitario de Tonalá from the University of Guadalajara, and Jesus Alejandro González Garcia from University of Flensburg in Germany, and Veronica Lisette Robles Dueñas from the Data Analysis Center and Supercomputing from the University of Guadalajara. What we want to present now is how could green energy be supply energy in a HPC data center. As you know, the HPC data center consume a lot of energy, and the cost of processing in HPC is one of the determining variables for its implementation and operation. So with the energy consumption being one of the most significant operating variables due to the high energy demand required by the different HPC equipment, so we make a model to analyze how the improvement of green energies could be reflected in the cost of processing in taking the model of node processing in HPC. So one of the alternatives to improve the energy consumption is use of renewable energy. As we know, each data center has different variables, different equipment, different air conditioned systems. And we have in Latin America different HPC data centers that have different conditions of improvement the building. So in that way, we decide to analyze the cost of processing in HPC data center as one of the how to describe the energy consumption by node, and how the green energy could be described in each of these nodes. How we do this? The implementation of the HPC data center have a lot of variables. So we make analysis of these variables based on different research that have direct inference on the consumption of energy. Which one are these one? The data equipment from the building and the data equipment from the technology information. Sorry, this is not in English. So with the arrival of these variables, we can have some difference between how to analyze this equipment. And we decide that we divide the CapEx and the OpEx cost. And with that cost, we have separate the cost of the energy consumption for each node. How do we do that? Well, this actual article proposed analysis of energy consumption by each part of these variables of the data center. We have this analysis focused on the consumption and HPC data center that we can see here in this line. The building cost and the IT cost is made by the all the implementation that have the building, air condition, processing, network, all the things that have some energy consumption. And we have some cost about the green energy supply implementation. What does this cost? For our research, we use the case of the CATS, the Data Analysis and Supercomputing Center of the University of Guadalajara. And for that specific data center, we can use solar energy because of the location, and they can put some solar panels to the location. And we have to divide that CapEx and OpEx cost in green energy supply implementation, emergency energy supply implementation, and grid for the connection for the grid. As you know, we have different ways to support the energy. So we have to maintain the service as long as we can install. So for this, we have a transfer box that have three supplies, three supplies of energy. That is a diesel plant, electric grid, and the solar panel supply. For this example, we use solar panel supply, but the model could be with aeolic energy or some else green energy support. The article proposed this model based on CapEx and OpEx, and the sum of that makes the TCO. And as we see here, we have three supplies channels, and also we have the battery supply. As you know, in the implementation, we need to, when you have the transfer box, we have to make a system that this change in the transfer can assure that there's no cut in the energy supply. So this is based on this equation. This equation is based on some other studies that has the CapEx and OpEx that in addition has the total cost of operation of a grid data center. The variables that we include here at the network is the solar panels and the aeolic energy, but for this case we use only solar panels. How do we analyze this? Well, we decide to separate each cost for each node and have a different monitor for each node. Each node has part, we assign part of the air conditioning system, part of the data network system, and the energy supply. These parts are the the energy consumption that makes each part. That's the way we can say how much energy does a node of HPC computer consumes in our data center. And the sum of each node will give us the total consumption of the data center in HPC. Why do we do this? Can assign to the jobs that are working the consumption and can make a projection for some years of this use. As you know, the implementation of green energy as solar energy have costs of implementation that make initial design of the data center make the cost higher for the implementation. But when we realize how to analyze this and how to say the green energy could be a good support to the HPC data center, we have to make a projection for 5 years. 5 years, 10 years, 20 years. This due to the life of the technology that are improved. As you know, the technology have some end of life in HPC technology, but the time life of technology as a solar panel is bigger. So we are trying to use this lifetime of the technology to apply to the 5 years that the life of the HPC data center could live. How do we do that? So we make an HPC data center TCO per node. So we made the total cost of operation making the OPEX and CAPEX per node and make it projection for 5 years. These 5 years could be assumed by a projection of energy consumed that make us see the CAPEX and OPEX for 1 year, 2 years, 3 years, 4 years, and 5 years. And we can compare this consumption when we have green energy implement without green energy improvement. This is the result of the first projection that makes us give us the CAPEX that is the cost of implementation goes up when you install green energy supply. So that is the first cost. So you can see at the yellow line that the OPEX is the cost that once you install, you have the energy supply from the grid that is increasing year by year. You know that in Mexico is the CFE, Comisión Federal de Electricidad, that has the billing every month, and you have to pay the bill. And every month you have to pay a billing based on the energy consumption. So what we are presenting here is that in 5 years, how this affects if you use green energy to supply your data center. This model shows in this graphic how in 5 years the cost of operation is what the cost is lower than using the grid, because of you don't have to pay the bill every month. But the way that you can see how this improvement can be reflected on your billing of each month is that you project for 5 years. If you see in 5 years you have a saving, a considerable saving in the OPEX of the energy consumption. How do we see that? In this place, we can see that the total cost of operation is the sum of CAPEX and OPEX, and you see that the total cost of operation that make green energy data center, that is TCOGE, is lower than the total cost of operation that if you don't have green energy. We know that it's not easy to put solar panels, and it depends of the geographical location, and it depends of the if you put aeolic energy, you have to have a special place to put the aeolic energy. So we make the study based on the HPC per node consumption. So this is what we can infer for 5 years of the total consumption of energy in each node for 5 years. So what we are improving here or projecting here is that if we can implement green energy for our HPC data center, have a considerable low cost for 5 years, and in 5 years you can see the reflex in your billing by month, how this affect and decrease this billing. But in the first year, you can see this improvement. When you employ the green energy, the first and second year, you can see this economy for each node. But if you project for 5 years, you can see that each node can be optimized and the energy consumption with the green energy supply. So what we assume from that is that the analysis of the total cost of the operation of an HPC data center can be determined by the cost of implementation and energy consumption. To know, this allows to determine the impact of the implementation of technologies of different kinds for supply and required processing. The impact of this implementation of this technology is in order to the availability of implementing green energy or the connecting to different grids or different billing supply methods. So this is it. I guess I'm out of time, so
okay,
I'm ready.
Thank you very much, Jorge, for your presentation. maybe the most important for all the data centers around the globe. So we are open for questions. As usual, you can raise your hand or write a question in the chat. Maria Ruiz Varela.
Speakers. So I think we have to address the very big elephant in the room question here. For those who might not know, in Mexico, the federal government has, you know what I'm talking about, right? Has sent an initiative or to reform the electrical current legislation that many of us believe would de-emphasize greatly the implementation of new energies and would set us back to rely on more fossil, dirty byproducts of petroleum extraction. So that obviously is not, we believe is not good for the country. And when I see this wonderful talk that we just listened to, that talks about the use of clean energies, I have to ask you, what are your thoughts or your fears regarding this legislation that it has a good possibility of being enacted? What would be the impact on all your planning that you're doing, that you're presenting here?
Well, the impact could be so hard. So one of the things that have or projection is that to use the legislation of the CFE, the Comisión Federal of Electricidad, to return the energy to the buying cost. But in the design that we use, the energy also can be direct supply the machine with the transfer box. So this model is based on the return of the energy to the CFE and goes down to the buying cost. But if, as you say, if these politics change, the only way that apply this model that we propose is that have the energy that we produce direct goes to the transfer box, but it implies some other transfer box that have the capability to make the change from the grid to the panel to the in this case diesel plant. So it makes it rise the cost of implementation. But the idea that we're trying to project here is that it's the impact of the green energy in the cost of processing. So if we have this change on the legislation, technologically will available to use this projection. It have a lot of technical issues that you have to implement, but that you have to put it in the analysis that we do in the capex cost, that is the building cost. I don't know if I answer.
Yes, Maria. Well, thank you. Any other question? Carlos Jaime Barrios.
Sí, hola Jorge, una pregunta de curiosidad. ¿El precio de la energía en Jalisco es más alto que en el resto del país o es más pequeña? ¿O cómo es ese costo de energía?
Varía por zona y por el tipo de... se hacen como tipos de consumos, y son, si eres, bueno, por el kilowatts que consumes, te dan diferentes tarifas por región y por lugar. Entonces, varía de estado a estado, varía de lugar a lugar y de pues ahora sí que localización.
¿Y para ustedes eso cómo les afecta? ¿Positivo o es negativo?
Bueno, así como está ahorita para nosotros es positivo por la ubicación que tenemos del centro de datos. Pero como bien comentan, si nos cambiaran las políticas, esperemos que no sea así, tendríamos que hacer un nuevo análisis para identificar esas variables y decir si sí nos conviene o no nos conviene el estar, este retorno de energía hacia la red eléctrica.
Ok, listo. Gracias.
I think we have time for last question from Isidoro.
Hola, ¿cómo estamos, Jorge? Muy bonita plática, felicidades. Yo nada más quería comentarte, o sea, bueno, yo veo que eso apenas es algo que puede ser plausible, pero hay un factor de colaboración que puede valer muchísimo la pena. Sinvestaves lleva la batuta hace tiempo en producir precisamente celdas solares para apoyar distintas ubicaciones masivamente. O sea, es una investigación que tiene ya 30 más o más años y tal vez valdría la pena que con todo el análisis que estás haciendo, estas son movibles, se pueden transportar, muchas de ellas, que se hiciera algún tipo de experimento o algo semejante en el cual se pudiera cotizar en base a esta infraestructura que se tiene junto con ustedes en algunos de los nodos y tratar de ver si ese tipo de camino sería una alternativa. La idea de los proyectos que se hacen en Sinvestab son precisamente para que sean de bajo precio, de llevar la electricidad, ¿sí?, a distintas partes del país, pero ya tienen producción masiva. Entonces sería tal vez interesante buscar un convenio de colaboración para tratar de ver si se podría realmente implementar al margen de las políticas de las que se están hablando, porque esto se podría hacer claramente como convenio entre instituciones y una vez que se vea el convencimiento y el cálculo, pues seguramente se escala, ¿no? Porque yo creo que la otra discusión es una discusión que va mucho más allá de cualquier cosa que podamos nosotros poner en la mesa, ¿no? Pero creo que es muy interesante y en vista de que ya tienes el trabajo hecho, yo te propondría con gusto que buscáramos los contactos para tratar de realizar algo así. Muy interesante el trabajo. Felicidades.
Muchas gracias, Isidoro. Y sí, bueno, sería bastante interesante que lo pudiéramos hacer. Y bueno, la idea es precisamente que no dependamos de esta legislación, sino que la generación de energía llegue directo a nuestro centro de datos sin tener que estar dependiendo de legislaciones que puedan afectar a esto. Y sí, con gusto, digo, yo te tomo la palabra y esperemos que podamos empezar a trabajar con esto.
Excelente, gracias.
Aprovechamos el tiempo. Hay una pregunta en el chat. ¿Su data center tienen alimentación de solo una subestación de CFE o más de 2 tributarios para redundancia? ¿Y con qué están midiendo consumo?
Se supone que tenemos dos subestaciones conectadas para llegar ahí al CATS, o al menos así estaban. Y, perdón, la otra pregunta es, ¿con qué estamos viendo? El video del consumo se pusieron, bueno, ahí tenemos un software para medición, pero para el caso de esto, de parte del doctorado en agua y energía de Cotonalá, se pusieron equipos de medición en el centro de datos, en los bordes de entrada de las diferentes partes del centro de datos, y aparte analizamos, como decía, de manera individual los consumos de cada nodo y del aire acondicionado.
Okay, so perfect. Thank you very much again, Jorge Lozoya, for your presentation. As you can see, it was very interesting, especially in Mexico in this moment. Yes, but we have to move on for the next presentation. So thank you very much. The last presentation for today is from Fernando Furusato. He is from the Brazilian Synchrotron-like Laboratory, Scientific Computing Group, and Data Acquisition and Processing Division. And the title of his talk is Throughput Enhanced Processing Unit, High Performance Computing Infrastructure for Beamline at Brazilian Synchrotron-like Laboratory series. So, Fernando, many thanks in advance for your presentation, and you have 15 minutes and after time for a couple of questions. So thank you.
Okay, I'll try to be quick. Hello, everyone. So I'm just going to present to you our infrastructure, our HPC infrastructure. So this work is an effort by me, Fernando Frussato, Eduardo Michelis, Gustavo Aranha, and Nascimento from the LNLS, and Luciano Zago, who is a master's student at Unicamp. Okay, so what is LNLS in Sirius? Well, Sirius is the particle accelerator, and also this structure that you can see on the right. And LNLS is the name of the lab in Portuguese. It's the Brazilian Synchrotron Light Laboratory. And the Sirius is the newest Brazilian synchrotron light source. It's currently the large scientific infrastructure in Brazil. And it's open to the scientific community, meaning that if a researcher or a research group want to use our facilities, they must send a proposal that will be analyzed and evaluated by the board and eventually approved if it fits the facilities. And as one can see, it was a very complex and thoroughly planned building and construction, and it took some years to get to be ready to use. Anyway, so what is the PUI? The PUI stands for Throughput Enhanced Processing Unit, and is the name of that we gave to the infrastructure, the HPC infrastructure. It's named after a South American geological formation, which is a type of mountain. It's, in my opinion, similar to a plateau. Anyway, it has three major subsystems, the S, B, and C subsystems that I'm going to talk about further in this presentation. And it has basically 10 processing servers, computing servers, out of which 5 are part of a cluster. But you can see in the figure that these are also servers, but they are not in the data center. They are in the beamlines. And also we have a 2 petabytes storage system that is set to be expanded next year to 4 petabytes. So what are the beamlines? They are the experimental stations where the data is generated and collected. So they process and send data using our infrastructure to the storage. But they also have local processing that happens within the beamline itself. They have a server there that processes data, and they can do all the processing there and just send the data to the storage unit. But when the data is too overwhelming for the local server, or they want to process it afterwards or reprocess the data, they can do that on our cluster. These are just pictures that, so you can see what it looks like, what a beamline looks like. This is a vacuum tube where some measurements are made in the Carretero beamline. And on the left, you can see the Carnaúba beamline station from the outside. So when I say data, what I am talking about, so all the servers have 200 gigabits. They are enabled to be connected with a 200 gigabits per second connection to the data center. And the data generation can reach up to 80 gigabytes within a few seconds, meaning a few terabytes of data in an hour, but it's the worst case scenario. These happen and processed into the TPU infrastructure, and they must be processed in a timely manner, meaning the user can process all the data, run image reconstructions and such, and take their data home. And this is just an image. It's a little confusing, but the data center is just this part here, and these are the connections. So the processing happens here. This is a picture of our data center. So this we call it island. The closer one is where the cluster is located. The middle one is where the network infrastructure is located, and the furthest one is where our storage unit is set. So not only we must have a good infrastructure, but the algorithms are very important. So we also have a group, a team that writes algorithms, they develop algorithms, and write code that are optimized as one can be to run there. So, I mean, they write parallel code and memory-aware code, so everything can be done in a timely manner. Also, we have that robust hardware configuration with CPU, GPU, and memory enough to do that, and a proper network infrastructure so we can transfer the data. So about the HPC subsystems, we have 3 of them. One of them is the P subsystem, P for processing. It's basically our cluster. It's composed of 5 NVIDIA DGX A100s, and they are in, that cluster is managed by Slurm. They are primarily running the processing in GPUs. And Slurm is the job scheduler, so you have a logging node where you can send the jobs to be executed on the compute nodes. The other subsystems are the S subsystem, which is the segmentation and visualization subsystem. That subsystem is set so one can use graphical interface, for example, to perform label annotation for image segmentation. So this image just illustrates that. This is an image of a segmentation of a sample from one of the beam lines called Mogno. And we also have the computing subsystem, the C subsystem, in which we for now just have one node, but it's a fat node. We call it fat node. It's enabled for 448 threads, processes actually with hyper thread enabled, and it has 6 terabytes of RAM. And it's of course better for CPU parallelism since it doesn't have any GPUs in there. Our storage system is 2 petabyte Cray Cluster Storage 1000 by HPE. It runs on Lustre file system, which is a parallel file system, and we enabled project quotas, which helps us manage the quotas for the groups or users who can send their data to there. And we also have what we call gateways that just translate the Lustre to other protocols. So when we access the data, we don't have to install Lustre client on every machine. And that's not really necessary since sometimes you just have to, you just want to download some data and it doesn't need a parallel file system. And it's currently connected via 100 gigabits per second connection to the core, but it can be up to 400 gigabits per second. And about the access management, we have an in-house system. We used to do that manually in the past, but we ended up developing our own system, our own software. That's because we didn't find anything that fit everything we needed. So we were in a rush, and so we ended up writing a a code, and it just grew from there. Anyway, it's called SAGU in Portuguese. It's user scheduling system in Portuguese. It has a web front end where the schedulings are done. The clients are the servers where they run. There's a daemon running on each of the servers. It stores the data in a MongoDB database, and it also manages some software licenses. Meaning they run on the licensed server machines. And the scheduling is managed by SAGU that I just talked about. For that, we have a predefined policy that says if how long a user can be scheduled, for how long a user can be scheduled, for the maximum time they can schedule their time on our infrastructure, and so on. And that is that picture is the picture of the front end, the web front end, and that is actually accessed by an end user who is from another group and is not familiar with command line interface. So we just developed that for them. It's the Beamlines user support group. So there they can schedule the users to use our facilities. And we also have a monitoring system. It's called Salmon. It stands for Automatic System for Logs, Monitoring, Analysis, and Observation in Portuguese. So in that system, we use Prometheus for data gathering and Grafana for plotting. And we also developed an API, so it's not bound to Grafana only. A user can just get the data and plot the way they want. And these are just some statistics of users. So the first one, then the plot number 1 is the total number of proposals, is just a cumulative histogram of every proposals we had so far for our facility. The number 2 is the total number of schedules along the time that we had so far. So it's past, I think it's past 4,000. The plot number 3 is just shows almost like a per day schedulings. So you can see some values that are probably weekends or long periods without working days. And number 4 is the same as number 2, but split up to each of the beamlines that use our system. And this finishes the presentation. Thank you. Please ask any questions if you have, and if you want to send an email, you can just reach us in those 2 email addresses. Thank you.
Thank you very much, Fernando. Especially for Latin America, this is an impressive infrastructure. So thanks again to all of you. We have time for a couple of questions. So you can raise your hand, write the question in the chat. No, there is no questions. As far as I know, in Mexico, we are also building a synchrotron. So in your opinion, which is the most difficult part, or just thinking it will be the thing that we have to take care if we want to create kind of the same infrastructure in Mexico?
Mm-hmm. Okay. We have a few difficult parts, like for one, managing the users. At first we didn't know how to do that, how to provide access and cut when the user stopped using, their schedulings ended. So we ended up doing a lot of manual work, and we just automated those, like cutting SSH access and such things. Another thing was when users want a graphical interface, they want to access a software that has a graphical interface. How do they do that remotely? And one of the most difficult things was when they tried to run an OpenGL application, which needs a local screen, and we had to think about that. And also how to handle all the data that are generated by, especially for image beamlines, because their data is very large and they have to process them very quickly. So these are some challenges that we faced and are facing right now.
Yeah, sure. Okay. Do we have any other question? It seems no. So this was the last talk. So I have to thank again to all the authors. So thank you very much again. And but also to the participants and all the technical staff. So thank you very much. Continue just enjoying the presentations from CARLA2021. And thanks. Have a nice day.
Thank you,
Bye-bye,
Luis.
Luis. Pleasure to meet you.
Thank
Bye-bye,
you,
everybody.
Bye.